Welcome to part 3 of the Hugo RAS Demystified series. This series that we just recently started, and in this section we'll examine the eyes of the Hugo robotic-assisted surgery system. We're going to learn about the vision stack and the imaging chain. And surgical robotics depends as much on sight as on motion. Every action robotic arm performs, it is guided by what the surgeon sees through the camera and display system. Hugo's vision architecture unites several technologies: a 3D high definition camera, an intelligent image processing tower, and an integrated endoscopic pathways that deliver clarity from deep within the body to the surgeon's open console. This focus of this module is how these pieces communicate, how light, optics, and digital signal processing work together to create real-time, accurate images with minimal delay. By the end, you'll understand how Hugo's vision system translates raw light into meaningful depth and texture, an optical symphony that turns precision mechanics into surgical artistry. The vision architecture of Hugo is built as an independent yet synchronized subsystem. It begins with the optical capture layer, camera heads, and endoscopes feeding high-definition video signals to the vision tower. Inside, processors render stereoscopic images, aligning the left and right video streams for perfect depth perception. Every pixel travels through the tower's processing chain, where latency reduction and color correction algorithms ensure real-time response. The system's modular structure allows components like camera control units or processors to be upgraded independently without disturbing other modules. Integration with the robotic arms ensure that as the instruments move, the field of view adjusts seamlessly. This kind of engineering precision is what allows surgeons to trust what they see. There's no lag, no distortion, just reality rendered with surgical clarity. At the heart of Hugo's imaging system is a series of components that each play a distinct role. The camera head captures light through twin optical paths, two miniature lenses that deliver the left and right perspectives that needed for 3D vision. The camera control unit manages exposure, gain, and signal integrity, ensuring consistent brightness and color across varying tissue types. The light source, often LED based, provides cool, uniform illumination to avoid tissue heating. Image processing occurs inside the tower. Digital filters enhance contrast, and adaptive algorithms maintain consistent tone even in low light conditions. Finally, synchronized output is distributed to multiple displays: the surgeon's console, tower monitor, and external visualization systems. This chain forms a closed feedback loop where optics capture reality, processors refine it, and displays present it with precision that makes microscale movements feel natural. The 3D HD camera is where perception becomes precision. Using dual optical channels, the system captures slightly offset images, one for each eye, creating a stereoscopic effect once processed. Inside the camera, high-definition sensors convert photons into digital signals, which are synchronized and merged by real-time algorithms within the tower. The result is true depth perception, allowing surgeons to judge distances and tissue planes with natural accuracy. The camera's design emphasizes balance and usability. It's lightweight to minimize strain and compact enough to fit seamlessly in robotic arms or manual holders. Temperature control within the housing ensures sensor stability, avoiding image noise during lengthy operations. Together, these innovations make the 3D HD system not just a camera, but an extension of the surgeon's own eyes, responsive, calibrated, and human-like in the way it perceives space. Endoscope integration completes Hugo's visual pathway from patient to console. The system supports both rigid and flexible endoscopes, depending on the surgical specialty. Light travels from the tower's illumination module through fiber optic bundles, entering the surgical field as bright, even illumination. The returning image passes through lenses and filters before reaching the 3D HD camera sensors. Each connection, mechanical, optical, and digital, is standardized, enabling quick setup and secure locking during docking. Calibration software aligns the endoscope's optical axis with the robotic arm's coordinate system, ensuring the image direction matches the surgeon's perspective. Materials are autoclavable, maintaining sterility without degrading optical coatings. This design allows Hugo to adapt across ENT, urologic, and laparoscopic specialties, proving that precision vision is as much about flexibility as it is about fidelity. Once light becomes data, the challenge shifts to managing that information efficiently. Video signals from the camera control unit enter the tower through high-speed digital links, where they're decoded and processed in real time. Advanced compression preserves full HD quality while minimizing data load on internal networks. Each frame is synchronized through instrument motion, eliminating perceptible lag and keeping the visual field perfectly aligned with robotic response. The processed video can be routed simultaneously to multiple displays, the main console, assist monitors, or external recording systems for teaching and analysis. Built-in redundancy ensures that if one pathway fails, another maintains continuous imaging. This careful orchestration of data flow ensures Hugo's visuals remain stable and responsive, every pixel exactly where and when it should be. Surgical imaging is only as good as its light. Hugo's illumination system uses high-efficiency LEDs that deliver intense brightness without the heat associated with traditional bulbs. The light passes through fiber optics into the endoscope, illuminating deep cavities with uniform coverage. Automatic gain and exposure controls adjust brightness dynamically as the scene changes, from dark tissue to reflective instruments. Color balancing algorithms continuously calibrate hue and saturation, maintaining a natural appearance under all conditions. Anti-fog coatings and active airflow prevent condensation on the scope lens, while digital filters enhance fine structures for visual clarity. Together, these systems create consistency. Surgeons can trust what they see is accurate, whether under bright operating lights or subtle micro movements deep within tissue. Ergonomics in visualization is about sustaining precision over time. The 3D display at the console provides immersive depth perception without visual distortion. The image latency is so low that hand-eye coordination feels natural, preserving intuitive control. Adjustable monitor positioning lets each surgeon find a comfortable posture, reducing neck strain and visual fatigue during lengthy operations. Color contrast and gamma settings are optimized to keep eyes relaxed even through hours of focus. Integrated tracking ensures that the display orientation remains aligned with instrument motion, minimizing disorientation when cameras pivot. The open console design allows easy communication with assistants and anesthesiologists while maintaining concentration on the display. These ergonomic refinements prove that precision isn't only about hardware, it's also about how comfortably humans and machines share a workspace. To keep image fidelity high, Hugo's vision components undergo routine calibration. Stereo alignment is checked to maintain true depth rendering, while color balance is verified against reference charts. Optical surfaces are cleaned using approved non-abrasive agents, and the endoscopic channels are sterilized between every case. Internal diagnostics monitor the sensor drift, dead pixels, or overheating, alerting service teams before any issue affects performance. Protective filters at the camera tip prevent fogging and fluid ingress, safeguarding delicate lenses. All components meet IEC medical imaging safety standards, ensuring patient and operator protection. Maintenance is designed for simplicity. Technicians can replace or recalibrate modules quickly without removing the tower from service. A well-calibrated vision system isn't just about sharp images, it's about consistent trust in what those images reveal. The future of surgical imaging builds on today's clarity to achieve tomorrow's insight. Future versions of the Hugo platform aim to deliver 4K resolution within 3D visualization, enhancing texture and depth perception even further. Augmented reality overlays will guide surgeons by superimposing digital maps or anatomical landmarks onto the live view. Artificial intelligence will analyze images in real time, highlighting vessels, nerves, or tumor boundaries to support safer decisions. Advances in fiber optic transmission and miniaturized sensors promise even thinner, more flexible scopes with uncompromised image quality. Eventually, wireless data streaming may reduce cable clutter, giving teams more room and freedom in the OR. Every generation of innovation moves toward the same goal, bringing the surgeons closer to what they see, with clarity so natural it feels like sight itself.